Welcome to iPsolutions Skunkworks Laboratory. Today's episode, What's That Smell? We are going to investigate the ability to discriminate between several common gases using the Bosch BME688 MOX sensor, coupled with our proprietary discrimination algorithm that we will call Secret Egg Salad Formula. We are going to start with a description of our fairly modest test setup. Our test chamber is a simple fish tank, without the fish. We use a Raspberry Pi as the data acquisition controller. It communicates with four sensor boards, Bosch BME688 and BME680, and two Sciosense ENS160s. A microfan is used to disperse vapors. The ENS160 units contain four separate sensors. The BME680 and 688 include single sensors. Although we are acquiring data from the ENS160s, we will feature the BME688, partly because Bosch is our target audience for this video, but mostly because this is the most useful for our algorithm. Here we can see the test chamber from the top and from the front. The Raspberry Pi is velcroed to the top of the chamber. The four sensor boards are velcroed to the underside. I have flipped the top over so we can see the sensor boards. Our discrimination test is based upon three gases: ethanol, ammonia, and isopropanol. We introduce the samples as liquids into the chamber. What is detected by the sensors are evaporated vapors. Discrimination metrics have been developed from a set of multiple exposures of each gas. The discrimination test is conducted on a new data set, which has not been included in the training set. In addition to the metrics associated with the three gases, we've also developed metrics associated with the baseline, which corresponds to plain air, and is acquired prior to the introduction of the first sample. As already mentioned, version 1 of the algorithm is based solely on the BME688. I want to emphasize the fact that this is the first version of an algorithm that is still evolving. Just a side note regarding the ENS160 data. The signals are noisier than those of the BME688, and the discrimination potential is less. We are using a stepped heater profile shown in the next slide on the BME680. This shows potential, but is not as robust, so it is not included in the first version of the algorithm. This shows the heater temperature profiles used for the four systems. A smooth profile is used for the BME688 and one of the ENS160s on all four channels. A stepped profile is used for the BME680 and the second ENS160. The temperature range for the BMEs is 150 to 320 degrees C. The range for the ENS160s is 100 to 300. All data cycles include 120 points at an interval of 282 milliseconds, which results in a cycle period of about 34 seconds. This shows test progress as monitored on an external workstation that reads data as it is acquired. The display includes two plots. The one on the left shows the average signal amplitude for each cycle. The plot on the right shows the absolute humidity, calculated using measured temperature and relative humidity from the BME688. Purpose for monitoring humidity is to investigate the interaction between gas concentration and the humidity signal. This display shows the test period up until just after introduction of ethanol. Each sample is measured and added to a clean glass dish. Ethanol is quite volatile and can saturate the sensors, so the mix has been diluted to half strength. This is approximately the same concentration of a typical spirit such as vodka or whiskey. After the sample has been prepared, the chamber lid is slid back and the sample is placed below the fan for dispersal. You might notice a product placement in the photograph. Yes, V8 is a sponsor for this experiment. Surprise your mouth with a jolt of V8 in the morning. It is more than a bland fruit juice. It is 100% vegetable juice. Let the games begin. This shows the external display up to just after the time when the ethanol has been removed. Notice that the BME688 and channel 3 of the ENS160 reach equilibrium while the other three still rise. Note that it is not essential to reach signal equilibrium to achieve discrimination. However, We want to see how discrimination evolves as gas concentration and signal intensity increases. Also note that the humidity signal has increased with the gas signal. We will see that this is the case for the other two gases as well. In fact, the humidity signal has not responded to an increase in humidity. There is none, but actually is due to a cross-sensitivity of the capacitive sensor to gases other than air and water vapor. Now we have tracked the test progress to just after the second sample, ammonia, has been introduced. Notice that we have not waited for the sensors to fully recover from the first exposure. This is intentional. It is not simply due to my lack of patience, although that is a factor. But we want to see the extent to which the sensors can accurately discriminate without waiting hours after an exposure has ended. We have now tracked to just after the ammonia has been removed. This shows the initial response to the introduction of isopropanol. Now the isopropanol has been removed and the test has been terminated. Time to see how we've done. This graph is a bit busy, but let's walk through it. First, focus on the blue line, which corresponds to the baseline. Our algorithm predicts that the first portion of the test is baseline, which is of course correct. At about cycle 50, the baseline metric drops and the orange ethanol signal emerges. Ding, 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 we have another winner. The region between about cycles 75 and 105 is after ethanol and before ammonia. The predicted state is indeterminate, but you can see that if we waited long enough, baseline will emerge. The indeterminate state is most likely due to a weak, but still detectable vapor concentration. Between cycles 105 and 150, with the exception of a brief isopropanol spike, ammonia is correctly identified. The period between cycles 150 and 190, baseline is correctly identified. It seems that the ammonia concentration and corresponding signal dissipates faster than ethanol. The region from cycles 190 to 290 is correctly identified as isopropanol. Following isopropanol, baseline quickly emerges. We have another trick up our sleeves to avoid possible ambiguity between exposures. First, look at the plot on the top left. This is a plot of P sub 0, the average cycle signal magnitude that is used for real-time test monitoring, but now plotted only for the BME688. The plot on the top right shows the cycle-by-cycle change in P sub 0. This provides up and down spikes corresponding to exposure starts and stops. The spikes are most prominent for ethanol, but small spikes for isopropyl are still sufficient to be distinguished from the rather quiet background. The plot on the bottom left shows a notch filter produced from the dP sub 0. When applied to the plot shown in the previous slide, we get what is shown in the bottom right. This filter allows us to see only the interesting stuff when a gas exposure is occurring. And now for some concluding remarks. Again, this is only version 1, but the discrimination algorithm performs very well for the limited number of gases that we have tested. We are only using data from the BME688 smooth heater protocol in this version, but with further study and experiments, inclusion of step protocol results may enhance discrimination. The relatively quiet and stable signal from the BME688 has enhanced our ability to determine baseline metrics over multiple tests, help to determine gas-specific metrics with a relatively small data set, and enhance our ability to clearly distinguish exposure starts and stops from the data set. In this case, we have applied the discrimination algorithm after tests have been completed. We have done this to allow for examination of algorithm variance. However, once we have a fully mature algorithm, it would be a simple matter to apply it in real time. To advance to a product-ready version, we will need more testing with more gases, controlled environments to determine environmental effects, and the ability to monitor gas concentrations. We plan, as a first step, to calculate approximate concentrations with our current setup. I have a couple afterthoughts. This shows the results from the BME680 step protocol. Notice that the discrimination is not quite as sharp, particularly for isopropanol. Again, we have less experience with this type of protocol, so it is reasonable to expect that this may improve with additional study. We have not used data from the NS160. Let us briefly take a look at why not. This shows the results from the NS160 Channel 3. I am not showing channels 0 through 2, since their performance is significantly worse. There are two features of note here compared to the BME688. First, the signal is significantly more noisy. Second, discrimination between gases of interest is fairly weak. However, discrimination between VOC and plain air is fairly good. This now concludes today's program, but don't forget to have yourself some V8.